Thank you, everyone, for coming to the third Matroid discussion. And today I thought that I would actually review the previous axioms by writing it so as to slow the pace down a little bit. Otherwise, there would have been like 2 pages where of symbols that I would just fly through. So let's begin with a review of section 1 and 2. So a matroid, and this is just to slow the pace down a bit. A matroid M is a set E of n elements and a family I of subsets of E that satisfies the first axiom. We'll call it I1 now. It's just the trivial condition that the empty set is independent. I2, I1 is independent, and I2 is contained in I1, then I2 is also independent. And the third one, that's the really meaningful one, and the axiom that Whitney captured about matrices. If I1 and I2 are independent such that I1 is less than I2, smaller in size, then there exists E in I2 minus I1 such that I1 union E is in I. That is, you can grow an independent set. And of course, members of I are called independent sets, and these are the independent axioms. If you just came in and you're experiencing a sense of deja vu, I'm reviewing everything and this time writing it down so that, just to slow the pace down a bit. So after that, we have a set of definitions of the other terms used, a subset of E that is not independent is, well, dependent, okay? And 2, a minimal dependent set is called a circuit. And this is an unfortunate clash of terminology because the circuits here really correspond to the cycles in a graph. And circuit means something else in a graph, and that's something you have to always remember when doing matroids. A maximal independent set is called a basis. Great name here. And what we did last week was the rank function. The rank function R is a function from the power set of E, that means all the subsets of E, to the natural numbers, where rank of X is the size of the largest independent set in X. So the circuit axioms and this we did on the first day, first week. So the set C, which is the set of circuits, C satisfies the trivial condition here that the empty set is also is not in C. C2 is if C1, C2 is a circuit and one is contained in another, then they have to be equal. The example to be kept in mind here is cycles in a graph. You can't have a cycle contained in another cycle. And C3, this is a circuit elimination axiom. If C1 and C2 are circuits and there's an element in the intersection, then there exists a circuit C3 such that C3 is contained in C1 union C2 minus E. And there the example would be something like this, where you have, this is RE, and you can see that, there's another circuit in C1 union C2 minus C. And this is called the a circuit elimination axiom. So these, it's how, you just sort of call it this, so circuit elimination, and this is independence augmentation axiom. Okay. And after that, we did the basis axioms and the rank axioms, and we're almost there done with our review then. So here's the basis axioms. The set of bases satisfies. This is non-empty, essentially one axiom, that's the trivial axiom. If B1 and B2 are bases such that E is in B1 minus B2, then there will be an F in B2 minus B1 such that B1 minus E union F is a basis. And this is what we call the basis exchange axiom. This is exchanging one element for another. And then last week we did the rank axioms. Almost done. So what is that? The rank function satisfies. Let's call them R1. That is, can be at most the size of X. R2, also very natural. For every X in E, if Y is contained in X, then the rank of Y is less than or equal to rank of X. And the third one is a submodular. Rank is a submodular function. And if you go to Wikipedia, there's a whole page of fascinating stuff on submodular functions, if you're interested in that. So this is submodular function. And the example we had, the first example that we did.
Sandra, 1 minute. Exactly what are the X's here? I'm not sure
X is a subset of E. They're all subset.
Yeah. Okay.
Yeah. And the first example that we did was uniform matroid. We're going to add a fourth example today. URN, where R is less than or equal to N. So here the ground set is just N elements, right? And then the independent set was the set of all subsets of size less than or equal to R. And the basis would be set of all subsets of size equal to R. And circuit would be set of all subsets of size equal to R plus 1. And what would be the rank? Rank of X would be just X if X is less than or equal to R, and just the rank of M if, and rank of M is just R here, if X is strictly greater than R. So our new example is going to be, let's call it example 4. I have example 2 and 3 on the next page. I want to put example 4 right here. It's going to be of what is called a paving matroid. And this one is, if E equals 1 to n again, but let's see, be the set of all subsets of size r, or r plus 1. So it contains the uniform matroids. So the uniform matroids are a proper subset of that, right? The circuits are not just size r plus 1, as in the case of uniform matroids, but also of size r. And there's this conjecture for which quite a bit of evidence has accumulated. Well, I don't know how much evidence, but a non-trivial amount. Almost all matroids are paving matroids. And again, Wikipedia has a page on paving matroids, and on that page there are several examples, and then there's a discussion of Steiner systems, which is what I'm hoping to do next. Not next week. We're not meeting next week, but the following week. After the concepts that we do today, we'll be able to talk about designs and stuff. So it's like yes.
Is there some intuition why the word paving is used in this context?
Oh, that's a good question. I think there was something. I think Welsh named it paving. He wasn't the first to come discover it, but no, I don't know. I'll have to look that up. That's a good question. So let me make a note of that as what's the intuition for the word paving? And then, of course, we have our example 2 and 3 of vector matroids that we did on the first day. That's a matrix, and then I is the set of all independent sets of columns of the vector space. So E is the column labels, and C is the minimally dependent set. This is the exact same example that you've seen twice, and this is the graphic matroid. Here you have the edges labeled, have to be labeled. So, this is edge, it looks like a vertex label, but they're all edges labeled. And then the cycles are actually the same as the cycles over there. So, matroid is like a perspective on graphs. So this graph G here is a sort of a representation of this same matroid of our example 2. Okay, so what's the plan today? We are going to talk about closure. So a new function associated with matroids. And hopefully today we'll sort of get done with the axiom systems and then branch out a little bit in examples and build up the theory. So let M be a matroid with ground set E and rank R, rank function R. So you should say rank function R. The closure function so defining another function is, what should we call it? I'll spell it out. Closure of X is a function from the power set, right, to also the power set here. And the closure of X, this is the closure function. I guess you could call it F. The closure of X is the set of all E in the ground set such that rank of X union E equals rank of X. So if some of this sounds like topology, and the language does come from topology, and you know, I actually have, like, we can talk about that in another session. But this is what how the closure function is defined. It's often called the closure operator. And let's look at the properties that the closure operator satisfies, and then those will become the closure axioms. And I think we are on proposition 10. Let the closure operator satisfies. And all of these are meaningful. So X is contained in its closure, right, for all X in E, the ground set. And always think of E as just a set of n elements, like that. 2, if X is contained in Y, then reasonable to expect closure of X is contained in closure of Y. And then 3, closure of the closure is well, the closure of X. Think closed sets in topology. And 4, this is the really meaningful one. So if B is in the closure of X union A, and B is not in the closure of X, then A is in the closure of X union B. So this is called the closure exchange property. And it sort of captures independence here. All of these axioms are going to be equivalent axiom systems. So 1 is good. Let's take a look at why 2 should hold. I should stop here and ask any questions. I think at some point we will use CL for closure, but when I write CL, it I don't know, it doesn't look like anything and causes confusion, so I just spell it out. Any questions so far, or should I just continue? We'll prove this. I actually have a proof for 2, 3, 4. Go through the proof. Okay, so we're doing 2. We have to show that the closure of X is so let's draw a picture. So here we have X and we have Y, and then we want to show the closure of X, and it's good to visualize it like sort of like a closure of X is just something around X like that, like almost like boundary points. And then this would be the closure of Y. So, you know, 2 seems like a reasonable property. Let E be a point in the closure of X, right? I mean, E could be here also, but let E be in the closure of X, and let B be a basis for X, right? Now, since rank of X union E is equal to rank of X, that's what it means to be in the closure. And if you want a visual example, maybe graphs is a good one here. So, you know, this edge, if you have this edge here, this green edge, in this graph, the blue edges are the spanning tree. The spanning tree is 3. So the rank of this graph is 3, but the green edge does not add anything to the rank, right? So rank of the blue edges together with the green edge would still be 3. So that's one example to keep in mind. So if E is in the closure of X, then rank of X union E is equal to rank of X. And that's how it's defined up here. Closure of X is set of all members that don't increase the rank. Then where are we? Since so B union E is dependent. And extend B to a basis B dash of Y union E. So B is a basis for X. So somewhere here is this B, that's a basis for X. And then you can extend it to a basis for Y union E. Now, rank of Y union E will be B dash, right? The size of B dash, we just said in the previous line, extend B to a basis B dash of Y union E. So the rank of Y union E is B dash, and that's the same as the rank of Y. So rank of Y union E equals rank of Y, and that means E is in the closure of Y. And that's it. So this is sort of the flavor of the proofs. If you know we were being very particular about proofs, this would be the flavor of the proofs. How are we doing on time? 4:25. All right. So the next one would be to show that closure of the closure of X is equal to closure of X. And I think here I have to move to a slightly shorter notation. It's just that this thing does not look, it looks anything like the C and the L that it should be. So, all right. So one direction, let's do this way. Since X is contained in the closure of X, right? Closure of X is a subset of closure of X. That's it. And then the other direction. Let's take E to be in the closure of X. I apologize, the CLs look like Ds or something. That's why I was spelling it out earlier. So rank of the closure of X union E equals rank of the closure of X, and that's the rank of X. But closure of X union E contains X union E, and that contains X, right? So rank of X union E is equal to rank of X. Therefore, E is in the closure of X. Just using the definition multiple times. And then the last one is a little non-trivial here. and is the one that captures the the heart of the closure axioms, the last one. So this is 4. And what are we doing in 4? Let's grab that statement down. If B is in the closure of X union A, right? So if B is in the closure of X union A and B is not in the closure of X, then A has to be in the closure of X union B. So, I mean, let's try and get a little picture going here. So you have X, right? And B is in the closure of X union A. So we're not saying that A is in X or anything. So somehow this is A and this is B, then B is like there's a circuit containing A and B, so to sort of. Then A will be in the closure of X union B. We're down in the weeds here. We will come up for air in a moment. So yeah, so B is in the closure of X union B union A, and B is not in the closure of just X. So we want to show this. A is in the closure of X union B. Well, so B is in the closure of X union A. What does that mean? It means that the rank of X union A and B, so we'll say X union AB, is equal to rank of X union A. All right, that's what by the definition of closure. And B is not in the closure of X, right? What that means is that rank of X union B is not rank of X. But it's not going to be small, it's a larger set. So rank of X union B is equal to rank of X plus 1. All right. And there's actually a little lemma over here happening that I could have pulled out earlier and said rank of X union B is the rank of X if X union B is dependent, or rank of X plus 1 if X union B is independent. So it'll just go up by 1. So this is little lemma here that I'm using. Okay, so where were we? Rank of X union B is rank of X plus 1. So rank of X union AB is rank of X union A, right? Rank of X union AB is rank of X union A. So we get that from here. And that's less than or equal to rank of X plus 1. And that is rank of X plus 1 is equal to rank of X union B. And so what do we have? We have rank of X union AB is equal to rank of X union B. Therefore, A is in the closure of X union B. Okay, so that's it. That was one direction of the equivalence of the axiom systems. So independent axioms are equivalent to the closure axioms. And we will skip this one, as we've skipped all the other ones like it. Okay, and now we come to closed sets of flats And and then very soon we'll have hyperplane. And now the hyperplane here means something different from the hyperplane in polytopes, and the flats also mean something different. So just something to keep in mind. Let M be a matroid with ground set E. Right? Let F be some subset of E. We say F is closed, or another word for closed is a flat. FLAT, if closure of F is equal to F. And S is a spanning set if closure of S is equal to E. And H is a hyperplane if H is a flat and rank of H is equal to rank of M minus 1. So that intuition of hyperplane being like a, if you're looking at Rn, the vector space Rn, the intuition of a hyperplane being, Rn minus 1, all the subspaces Rn minus 1 is still there here. It's the rank of H is just 1 less than the rank of M. Okay, so where are we? Yeah. And I won't prove this proposition. It just sets up all the relationships between the things that we just defined. So I is independent if and only if for every E in I, E is not in the closure of I union E. I minus E. And S is spanning if and only if rank of S is equal to rank of the whole space. And B is a basis if and only if B is a minimal spanning set. Hyperplane is a maximal non-spanning set. And a circuit is, C is a circuit if and only if C is a minimal non-empty set such that for every E in C, every element of C, E is in the closure of C minus E. All right. And 6, closure of X is the set of all X union E such that there exists a circuit C and E is in C contained in X union. So let's go back to that example that I did earlier. Let's suppose this is a graph. Then, here you have the spanning tree. And because it closed it up to form a cycle, I said that the green edge is in the closure of the blue edges, and that's captured here. It'll be X, and all the members, all the other edges for which there's a circuit entirely contained in X and just sticking out by E. All right, so the flats have a flat axioms, which we actually need for the geometric representation. And then the spanning sets and hyperplanes also have axioms. I think I skipped the spanning set axioms, but we do need the flat and the hyperplane axioms going forward to understand the geometric representations.
Sorry, could you scroll back up to the list of that proposition? I didn't get to finish writing it down yet. Thanks. I'm on 4 if that's relevant so that you have some room.
Yeah.
I appreciate it. I'll take a screenshot.
And I will actually post notes. I have better notes than this because I'm writing a little fast, so the notes are a little not so nice. I have very nice notes that I've written carefully out by hand with color and everything, and I'll post those notes. So, proposition 13. Let M be a matroid, ground set E, and let F be a set of flats. So what is flats? Flats are the closed sets, right? And those are all the sets where the closure of X is equal to X, right? So closure X is equal to X. That's what flats are in terms of the closure operator. The trivial axiom, the whole set is a flat. What F? Now, I, F. And then 2, if F1, F2 is in F, then the intersection of those two sets are also in F. And 3, so the intersection of every pair of members of F will also be a closed set. And this one, I mean, the third axioms in each of these axiom systems are just pure geniuses. And first 2 are fairly straightforward. If F is a flat, right, and F1, F2 to Fk is the set of minimal members of F that properly contain the beginning flat F, then F1 minus F, F2 minus F, Fk minus F, partition E minus F. And I need this when we do the lattice presentation of matroids. Matroids are actually geometric lattices. It's just another word for geometric lattices. Could have called them geometric lattices the whole time. And how are we doing on time? We have a little time, so we can kind of go through the proof. So we want to see the proof of 2 and 3, right? So these are the flat axioms. So far, so good. Right. don't hesitate to stop me as I'm talking and then just ask a question, all right? I kind of pick up speed as I'm talking and I can go unnecessarily fast. So we want to show that F1 intersection F2 is a flat. That means to show that it's a closed set, right? So closure of F1 intersection F2 is equal to F1 intersection F2. So in the geometric lattice presentation of a matroid, all the entries are flats. So, all right, how does this work? Well, F1 intersection F2 is a subset of F1, right? And F1 intersection F2 is also a subset of F2, right? So that's F1 intersection F2 in the middle here. So closure of F1 intersection F2 will be contained in the closure of F1. And what would be the closure of F1? It's a flat, so its closure would be F1 itself, right? And then here, closure of F1 intersection F2 would be contained in the closure of F2, and that would be just F2 itself because F2 is also closed. So therefore, closure of F1 intersection F2 will be contained in the intersection. Closure of the intersection is contained in F1 as well as F2 and therefore in the intersection. Good. So if you take two closed sets and look at the intersection, and it's got to be a closed set. And then think lattice, as in the intersection. You know, you have the join up and the meet. So the meet is the intersections. And now let's do 3. And yeah, this is the 3 is the amazing property here. So what are we trying to show? We want to show that it's a partition, right? So you have your flagged flat over there, F, selected flat. You have a set of minimal members of F. That means, you know, all the other flats that are minimally contain F. And you want to show that that partitions the E minus F. So we have to show that the intersection of these two things is, any two of these things is empty, and then the whole thing is the space, E minus F. So to show Fi minus F intersection Fj minus F is empty, right? And then the union will be also E minus F. But suppose it's not empty, right? Suppose X is a member over there. So a picture would be like this is F, and you have all these minimal non-empty flats containing F. So suppose there's an X in Fi minus F. And X in Fj minus F, right? So there's a member in F1 minus F and F2 minus F, for example. Now, Fi intersection Fj is a flat strictly containing F, right? And this contradicts the minimality of Fi and Fj. Because if you've got something in the intersection of Fi minus F and Fj minus F, then Fi intersection Fj would be strictly containing F, and that's a contradiction to the minimality. Then the next thing is to show that the union of these things, right? So union of all the Fi minus Fs will be E minus F. Now suppose X is a member of E minus F, and X is not in one of the Fi's for any I, right? So there's something here that's not, so there'll be some member here, X is here, that's not in any of the Fi's. Then closure of F union X is a flat containing F. Yeah, it'll contain F and should be in the list of minimal flats F1 to Fk, and it's not. So that's a contradiction there too. The contradictions are just one-line contradictions, but they give a very meaningful axiom. Right, so let's get a picture going to see that. So you have F1, F2, and also F over here. Say this is F. And there is an X somehow in the intersection. So it's in E minus F, but it's not in any of the Fi's. So a little hard to draw that is in one of the Fi's, but suppose there's some member here that's not in any of the Fi's. Then closure of F union X is a flat containing F, and that should be in the list of minimal flats F1 to Fk, and it's not. All right, that's it. So proposition 14, the independence axioms are equivalent to the flat axioms. I think one direction is done in all the things. It's the other direction that requires some work. I think in this case, the closure axioms are equivalent to the flat axioms, and then one direction is done. Yeah. And the last thing is the hyperplane axioms. We will be using the flat axioms and the hyperplane axioms when we draw our lattices next time. So let M be a matroid, and H is a set of hyperplanes. Then H satisfies the trivial condition. It means the whole space cannot be hyperplanes. Hyperplanes is one rank less than the space. All the closed sets that have one rank less than the space. All the flats with one rank less than n. And if H1, H2 is hyperplanes and H1 is contained in H2, then they're equal. And 3, if H1 and H2 are distinct members of H, and E is in the complement of H1 union H2, then there's a third member, there's a third hyperplane containing H3, containing H1 union intersection H2 union. I think I got that right, yeah. And basically there's it's a little intense, and there's a lemma that's required that we're not going to be doing. So yeah, so that's it. And I think I have a few minutes to do I have that? Let's see, I may not have it. All right, so in the last few minutes, what I wanted to do, so these are our cryptomorphic axioms. We're not doing any more. And this is it in terms of axioms. So maybe we'll do one more example, like it's a whole family of examples before we end. So we had uniform graph, matrix, paving, and now this one. So a linear space, that is what it is called. There's a whole book called Linear Space, and that's basically rank three Matroid, is a set of points E and a subset of points called lines. Don't think graphs, these are points and lines in the plane, incident structures, such that the usual properties of points and lines in the plane are satisfied. This is incidence geometry here. A line has at least two distinct points, and two lines intersect in at most one point. That is what you would expect points and lines in the plane to do. And then the non-trivial condition, there are at least 3 non-collinear lines, points. So the set F consisting of, what did we say, was the empty set of flat? Yes. The empty set, all the singletons, right? The endpoints, all the lines, and E. We can show that We won't show it now, but we can show that F is a set of flats. So this is how I like to introduce the geometric picture that I mentioned on the first day with U24 drew 4 points on the line. Points and lines. So these are sort of lines. Every pair of points. So I don't have to stop there. I can, how about this? Let me put points in the plane. Let me scatter 4 points on the plane, 4, 5, 6 points on the plane. It's just throwing 6 points on the plane. And then let me just, now every pair of points will determine a line. So we don't draw the 2-point line. So we won't draw, something like this where there's just a line between a pair of 2 points, but we draw like the non-trivial lines. So that would be, this one here and this one here. All right, we want a line going through 1, 4, 2 and a line going through 2, 5, 3, and those are like the non-trivial lines. So those we'll draw. And it is customary to actually not have these lines extend like that and just look like this. So now when I draw this, it looks like a graph. And in context, you have to know it's not a graph. This is not a graph, not a graph. So these are, I'll say that again, you just scatter a bunch of points on the plane, 1, 2, 3, 4, 5, 6, right? Between every pair of points, there's a line. So there's a line here, which is not drawing it. There's a line here. There's a line here. There's a line between 1, 4, but that one also passes through 2. That's a non-trivial line that we'll draw, and so on. So there's lots of lines here. We're only drawing the non-trivial ones. And then this figure, we, instead of drawing it the way I did it on the left, we actually draw it like this. So what would be the flats? Well, we can break them up by a rank. The rank 0 flats are the empty set, right? The rank 1 flats are the singletons, 1, 2, 6, right? The rank 2 flats are the lines. These are the lines in this incidence geometry. And the non-trivial ones are 1, 2, 4, and 2, 3, 5. And then you have all the other pairs, like 1, 6, 2, 6, etc. And then the rank 3 flat is just the whole space. And then this you can draw as a lattice. So the empty set, so we're making a transition now from a big transition, the one that I think Birkhoff did it. He was the one who said it's a geometric lattice. So this is, so let's do a Hasse diagram of a lattice. So we have 1, 2, 6. And there's lots and lots of these pairs of points. I only put down a couple there. But 1, 2, 4 is a non-trivial line. And actually that's 1, 2, 4 is a circuit here. 1, 2, 4. And 2, 3, 5. And then all the trivial lines like 1, 6, that would be this and that. And 2, 6, this and that, and lots of them. And then all of them, this is So yeah, it was Birkhoff. 1935, Birkhoff. This would be, I think, proposition 17 is Matroid is really geometric lattice. And you can do this in any rank. I mean, rank 3, we can draw these nice pictures on the plane. Rank 4, so we have some pictures that we can draw, but this limited. But then you can just do this for any rank. And yeah, so this basically, so in that sense, Matroids is an older topic than 1935. Now we're talking about points and lines in the plane. And I'll just say one more thing before I end. I read Hilbert's, I think it was Foundations of Geometry, and the first chapter is called Configurations. And I was always a little bit fuzzy about this until I read that chapter. But his configurations, a line can have just 1 point. So he allowed 1 point lines. But still, the way he wrote that chapter, I thought was excellent. I have to confirm the reference. I think it's his Foundations of Geometry book. Yeah, and very soon we'll be talking projective geometries. And all right, this is a good place to stop. I'll stop the recording and